Is it okay now? Just check. Share. Okay, good. So why drill directional wells? Sidetracking are performed in situations where drilling cannot be continued due to a fish in hole, or to explore a different area, or to make multiple producing wells from the main well bore. So the main problem in requirements of directional well is that, for example, if you have an urban area, you have a railway system, you have a difficult terrain, as you can see in the image, they're considered as inaccessible location. And with that, you might find it difficult to drill vertically, because you are already got buildings, or you got some river or anything like that. That is not where it's not possible to locate a rig. So then you have to drill a directional well. And then sometimes we may have a salt dome. These salt formations are considered to be natural, traps for hydrocarbons, because they act as a cap rock. And there are several drilling problems associated with salt dome. So sometimes it is required to avoid the salt dome. And as you can see in the image, instead of drilling vertically through the salt dome, in this situation, it has been decided to drill from the side of the salt dome into the hydrocarbon reservoir. So essentially, every effort is made to avoid drilling through the salt dome. But there are cases where we have to drill through the salt dome and make sure that you reach the target. So you do drill through salt, but it is considered to be very challenging. Sometimes it's also called as fault control, where you need to control the well and avoid drilling through fault. Again, fault can cause huge problems. They are usually, suddenly there is a change in the pressure regime, and it is not possible to control the well in such situations. So there are cases where we need to avoid drilling through the fault. So you drill from the side and into the reservoir directly, as can be seen in the schematic. Onshore to sea, sometimes if it is not possible to get an offshore rig, or it is easier to drill from onshore, then it is considered to be cost saving technique, to drill from an onshore location. So you locate your rig on an onshore location near the sea, and then drill a deviated well. As it can be seen, there are numerous cases like this where we drill from an onshore location. So multi-lateral wells, enables numerous legs. You can drill multiple from the same motherboard. You drill various different laterals into different target reservoirs. So the advantage of this is that you save on the number of wells. So from the same well, you can produce from different layers, and as one layer depletes, you transfer your production to the other layer. So you save cost on the drilling. Drilling cost, as you know, is quite high. This multi-layer wells technology is quite complex. It is in use, but it still requires high precision in terms of directional drilling capabilities. But to say that it is not possible will be a hard statement. Multilateral wells are being drilled, but people, because of the complexity, they generally avoid drilling it. But I have been involved in multilateral wells in Saudi Arabia myself, so it was done pretty, smoothly. Now, this is an offshore well where you have a slot, and from there you drill from the platform. You have a platform rig, and you drill multiple wells from the same platform. In shallow waters, this is a very common practice in offshore shallow water drilling, where you have a platform and you have one template from where you drill multiple wells. There also you need directional drilling, obviously, because you need to drill in different directions. You cannot drill in the same direction. So this is how you drill multilateral wells. Now the directional drilling becomes more complicated in such situations because there is an issue of collision. Collision meaning you might end up, if there is a minor error in your coordinate system or in your measurement, which we will talk about a little later today. then you can collide into another well. And so in this kind of situations, you need to do anti-collision studies. So this is also in the scope of directional drilling. A directional drilling professional needs to run some modeling and do anti-collision analysis and let the company know how close you would be getting to another well, which may be a producing well. And imagine if you drill into a producing well, it can be a disaster. Now, one other application of directional drilling. So what we are discussing is why we need to drill directional wells. Now, here is another example of why we need to drill a directional well is to drill a relief well. Now, you see here in this image, there is a blowout. The well is blowing, and there is no way you can control this well from surface because there is a lot of fire. So you drill a deviated well and very precisely you intersect this well at certain depth in the high pressure zone, as can be seen in this image. And then you pump heavy kill mud and cement into this well. There is a process involved in that. Relief well drilling is a very complex process. It's a very challenging and highly competitive business or area of work. So relief well drilling and planning is and then because you are typically dealing with very precise tolerances and higher pressures and all that. But you need to do that, and it is done routinely in case if you lose control of the well and you need to kill a well, a blowing well, then you need to drill relief well. The example of relief wells are Macondo, in Gulf of Mexico, where we had a blowout in BP. So they had to drill a relief well, and eventually the well, that blowing well, was capped after several months. I think 1 or 2 months using a relief well. And then this is how it is basically killed. It takes a few months, sometimes more than a month to kill. The other type of application of directional wells is SAGD wells. This you may or may not have heard, but this is an enhanced oil recovery technique called SAGD. So this is steam assisted gravity drainage. It's a part of enhanced oil recovery technology, and where you have heavy oil and bitumen, this form of wells are drilled, where you drill 2 wells parallel side by side, as can be seen, and it isn't it's also called as steam stimulation, in which a horizontal pair of well is drilled in oil reservoir, and one is drilled basically the distance between the two is about a few meters, and the high pressure steam is injected in one well. Basically the upper well, and this causes the heavy oil to become mobile and then flow in the lower well. This is a very advanced technique that is used nowadays as part of enhanced oil recovery method. And I encourage all of you to kind of read about this and do some research. A lot of work is being done in this area. So what are the different types of directional wells? So there are different types of directional wells. One is build and hold, and drop, continuous build, and then you have horizontal wells. So there are 3-4 types of profile that are available. So what are the requirements of directional wells? There are some preliminary requirements, and the first thing that you need is a deflection tool in which you can actually change the path of the well from horizontal to vertical. Now, as you can see here, you need some kind of a tool in your bottom hole assembly that will cause your well to deviate at a certain depth, and you need to orient it in a particular way. So different tools that have been used by the industry, deflection tools that are used that can cause a drill bit to deviate, followed by to follow a preset, follow a trajectory. There are Whipstocks, for example. There are jet bits with oriented nozzle. There are downhole steerable systems, and then there are conventional BHA hookups. Like you can have your BHA configured with your stabilizers in a way that when you apply certain weight on bit, the BHA will orient in one direction. So using stabilizer configuration, you can deviate. So there are some of the arrangements, but the most popular ones is the downhole steerable systems. That is the use of motors. The jet bit orientation and oriented nozzle is an old method, and it's not very successful, or it's not very commonly used. Whipstocks are used in cased hole where you need to sidetrack from inside the casing. In open holes, directional wells, most common application is stirrable systems, where either you use a motor or you use a motor, or you use a rotary stirrable system. So this is what the whipstock is that I just spoke about. You know, as you can see here, in case of mainly used in cased hole, and some of them are retrievable, some of them are permanent. So you actually have a base and a whipstock where you orient your tool inside the casing from where you want to deviate, and then you have your whipstock assembly here, a bridge plug which is set at a particular depth, and then above that you have your milling assembly here, as it can be seen. The milling assembly will continue to drill, and at a particular point it will sidetrack. In this case, we have seen a watermelon mill. You know? And then you pull out this and go with another VHA. So jet bit application in soft formation. Sometimes if you have very soft formation, you can use this configuration where you plug one of the bits, and using other, just nozzle, one of the nozzles open, you orient your, direction, orient your BHA to the desired direction, and you sidetrack the well. Now, the other two important types of systems are positive displacement motor, turbine motor, and then you have also rotary stirrable systems. So RSS cause a deviating force against the side of the well bore to push the bit inward along the preset path. So it will move. It will cause the bit to move in a predetermined direction. This is a very advanced form of directional drilling, where you can actually change the direction of the well as you're drilling by sending a command, which they call it as downlink. But the most common ones are positive displacement motors. They're like this. They appear like this. You have your stabilizer, your dump valve, your power section, your bent housing, and your bearing housing, stabilizer, and then your bit. And here you see in your power section how you can have different configurations depending on your torque requirement, power requirement, basically. So this is how you need higher power. You have more, loops, as they call here. Again, today's session is an overview, but we will have an opportunity to discuss all this in details in our course. And therefore, I would all encourage you to register for the course. It's a 6-day extensive course. We will be discussing about all these things in really great details. And we'll also do a number of calculations and numericals and other things. We will have some assignments, some quizzes, and all that. That will ensure that your fundamentals are very well built, around directional drilling, and you can take upon any sort of assignment, in the future. So normally in summary, what are the requirements of directional well? So normally you have downhole stirrable systems and measurement while drilling. You have deflection tools. You have higher hydraulics. You can generate higher hydraulics using a motor that can help in better hole cleaning. Then you need to do some engineering calculations for directional planning, and we will come to that in the next few slides. So the engineering planning and all of that is a highly important part. You make a plan, you run simulations, you make a plan, you discuss with your customer as to whether the plan is, whether the trajectory that you have designed or built is suitable and can be used, or if there are any issues, then you have to go back and change your plan. So these are the things that you do. Then you select your BHA, what kind of bottom hole assembly you're going to use. The bottom hole assembly can change while you're drilling, while you're through the course. The BHA should transfer the weight, and this is a very typical issue in highly deviated wells, where the weight is not transferred on the bit. And as you know, in a lot of cases, you need to have it on bit to drill. So this is highly important. And then you need to have some other things like rubber protectors for drill string to protect against wear of casing and drill pipe. You need hard binding of drill pipe sometimes, and we'll discuss that in the future why we need, because primarily in directional wells, sometimes a particular section of the well, you might be causing some casing and drill pipe friction, and this can cause wear in the metal, which is highly undesirable. So to prevent that from happening, hard binding is done, and also rubber protectors are used. Again, you need to add some lubricating additives to the drilling mud to reduce torque and drag in deviated and horizontal wells. And further down, once you run the casing, centralization of casing is very important. In vertical wells, it's important, of course, but in deviated well, it becomes more important because you want your casing to be in the center. You don't want it to be on the lower side of the well, because the casing, the cement needs to be uniformly distributed around the casing in order to ensure that this is a proper zonal isolation. The function of casing and cement is to isolate a zone. In the absence of cement, your casing might not get proper protection, and it can form some sort of a channel between lower part of the wellbore to upper part of the wellbore behind the casing. And if the cement is not there in place, this channel can form leak paths and compromise the integrity of the well. So with that, it is very important to have proper centralization. And this is one of the requirements of directional wells. So let's look at some of the basic terminologies in directional wells. What you have is what we call kickoff point. Then you have a build-up section. Then you have end of build. You see in the diagram here, at different points of a well, different terms are used. Then you have a tangent section. Then you have a start of drop section. Then you actually have a drop section. Then you have end of drop, hold section, and then you have a target depth. So these are some of the terminologies that you will come across when you're discussing the directional well planning or involved in directional well planning. And this course will help you get familiar with this, because you will do a number of calculations going forward. These calculations, you will be calculating certain things that are associated with the directional wells. Also, some other terms that you should be familiar with is the total vertical depth, the measured depth. You can see here in the image where TVD is just the vertical depth here, and this is your TVD here. You have your turn rate, you have your build rate, and this is your measured depth. The depth that the bit measures or the drill pipe, along the course of the well is measured depth, whereas TVD is just the vertical depth from surface to bottom. There are two different things in deviated wells, and one should be careful with the depths in order to get the calculations right, various engineering calculation right. So as you become familiar with these things, it's not very difficult, but in the beginning, it's important to know which depth to consider while doing certain calculations. You also have your inclination and azimuth. They are very important measurements when we take surveys, and you see if you are following the right trajectory. Turn rate, build rate, as I just spoke about. And then azimuth, is in reference to something what is called as azimuth quadrant, where you you have this quadrant and you measure your azimuth with reference to north, south, east, west. This quadrant, and then you have your number. Azimuth value, I mean. So different terms that are used is whole direction, and then there is also something that you should be familiar with is there are two types of north. One is the magnetic north. All your measurements are with respect to north clock, and then there is a true north and the magnetic north. Magnetic, and then the difference between them is called as magnetic deviation. And normally all of the measurements are done with respect to magnetic north, and then they are changed to true north. Because in case if you use a different system, then it needs to be available. Also, if you see here, there is what is called as build rate that we just saw here in this diagram here. So this is the build rate at which from your vertical, how you are building your angle. You know? And then again in that, there are three categories. One is the long radius, medium radius, and short radius. So this depends, the range of build rate is divided into these three categories: long radius, medium radius, short radius. Now here you can see an example: horizontal displacement, total vertical depth, and these are all the build rates, starting with 8 degrees to 25 degrees. You know, the higher the build rate, the shorter you have your trajectory. Higher the lower the build rate, your trajectory is bigger. You know. So you need to choose what build rate you want to have, and accordingly things will change in your directional planning. As I said, you know, as we go along, we'll discuss this in greater details and the implications of this. Let's talk a little bit about bottom hole assembly. Bottom hole assembly is very important in directional wells as it is in vertical wells, but certain components change in the bottom hole assembly in directional wells. And they are basically bottom hole assembly. You have your drill bit, you have your sub. So drill bit is the same as you would use in your vertical well. So not much change really in subs. There are multiple subs, type of subs, crossover sub, bit sub, etc. And in this subs, they will typically have NRV, non-return valve, which is used to prevent any backflow at the time of influx. Then you have drill collars. Again, drill collars, a large number of drill collars are used here in directional wells. You have non-magnetic drill collars, you have spiral drill collars, you have normal drill collars, and you have square drill collars. So in directional wells, you use a large number of different type of drill collars depending on your requirement. And you also have heavyweight drill pipe, stabilizers, measurement while drilling, you know, that is MWD, commonly logging while drilling, your mud motors, your drilling jars. So a number of things are used in a deviated well as part of the BHA. Then you also have stabilizers. I mentioned over here stabilizers. You can have hole openers, you can have reamers. So many different types of components are used in a BHA. So let's talk about a little bit about well control in deviated and horizontal wells. So why is it, what is different, and why are we concerned about this in horizontal wells? We are definitely concerned about well control in vertical wells, but what is it that is different? Now you see here, when you have a long section of hydrocarbons bearing formation exposed in a horizontal well, it can generate more hydrocarbons as compared to vertical wells because the number of sections is high. Now, accumulation of hydrocarbons and high spot in the open hole. So what happens is, if you have gas influx and you have a long lateral, the hydrocarbons can potentially accumulate on the higher side, higher spots. And if you have some dog legs or something like that, you can have some gas pockets. Gas can get accumulated over there rather than moving up the wellbore and to the surface. Since you have an unusual drill string configuration, stabilizers and stuff like that, this can cause some other issues, you know. And the position of casing shoe is important, and the kill method is also important to determine. It might change. So this can cause a high inflow of hydrocarbons because you have more exposed, longer section that is exposed. This can cause a high inflow. And that can lead to large volumes of hydrocarbons to come to surface because you have a bigger section of formation exposed. Like I said, greater area of reservoir open. And once borehole gets underbalanced, production will increase rapidly. So what they mean here, what it is meant over here is that as you unload the well with the hydrocarbons, it will quickly become underbalanced. And once your well gets underbalanced, because you have less mud in the hole, and then you also have some gas or oil, then your gas from formation will rapidly increase, and it will become very difficult to control the well. So this is an important point of concern, when you're dealing with horizontal wells. So there are two types of kicks, essentially that can be considered. One is underbalanced kick, where you have where we just spoke about, but then it can also cause because of a faulted reservoir, where the pressure might suddenly increase, and your mud system does not have enough hydrostatic pressure to counter, so you become underbalanced. The other point could be an induced kick in horizontal wells. So induced kick can be because of swap and surge effects. If there's a restricted annular clearance, because of cuttings bed in the transition zone, because of a loss of circulation, ECD can increase, suddenly, and loss circulation, higher swap pressures than equivalent vertical well. So in the case of loss circulation, directional wells can generate higher pressures in swap pressure as compared to vertical wells. So these are some of the points of concerns or somewhere or something that we need to pay attention to when we are dealing with horizontal wells, and they can cause an influx, and that needs to be controlled. So here you can see in these images, basically pinch out where you reach into another high pressure zone, or there is a fault, that we just spoke about. Now, as it can be seen here, there is a tendency of the cuttings to accumulate on the lower side of the well here, as you can see, in the transition zone or in the horizontal zone. So with this, you have very limited clearance between your well and your BHA. So as you're tripping out a hole, you can swab a kick in, and this is termed as induced kick. So here again in the schematic, what you would see is that the yellow part is representing a gas influx. So you have what we're comparing here is a horizontal well versus a vertical well. Now, in the horizontal well, as you can see here, your shut-in casing pressure and shut-in drill pipe pressure does not show any difference, because if you know, most of the calculations are based on TVD. So as long as your kick is in the horizontal section, as long as your influx in the horizontal section, your pressure, both of the pressures will be same, and there won't be any loss of hydrostatic pressure. So if you can see here, loss of hydrostatic due to lighter influx causing increased flow as the volume of influx increases. So there is a very gradual, pit gain in horizontal well as compared to vertical well, which is linear, and this is somewhat dangerous because your pit gain doesn't show any good indication in horizontal wells, although you have taken the same amount of influx. Because it is in the horizontal section of your well, your pit is not showing any gain. So what happens is, as I've discussed before, gas has a tendency to accumulate on the higher side of the well and elongate to the top side of the well. And if there is any breakout or washout like this, gas might go and accumulate over there, get trapped over there, which is difficult to circulate out. So you need higher circulating rates compared to your slow circulation rate. So you have to keep this in mind when you're dealing horizontal wells, that you might need to go higher than your circulation rates. Once the required influx is out, then you can go back to your circulation health. And you might need bullheading. Sometimes this doesn't work, so you have to do bullheading and push the formation back in, push the kick influx back into the formation. So these are some of the concerns that we have. Again, by no means we have covered the subject in details. We have one full day of class marked for this subject. This is just to give you an overview of the points, concerns that you have, in case if you are wondering, in case if you're thinking, what is it that is different in horizontal wells as compared to vertical wells when it comes to well control. So that is what we are planning to cover, and in our course we will also cover quite the subject in greater details. So survey tools. Now, what are survey tools and why is surveying required? So basically, directional surveys are taken regularly to calculate your depth, your position of the tool, and your angle and inclination, whether you're proceeding in the same angle as planned. So there are two types of surveying tools. One is your magnetic surveys, and then there's gyroscopic. So whenever there is a concern or a issue related to interference from any magnetic material, then you go ahead with the gyroscopic tools. Basically, inside casing, if you want to do any survey, you use gyroscopic surveys. Before you, and this also works as an alternative method of your magnetic survey, which is your standard MWD2. So you have both the options available. Now there are some survey calculations. Now, once you obtain the surveys using one of these techniques, you need to do some calculations to find your coordinates, to find where you are, and your total vertical depth. You have your measured depth, which is actually measured while you are drilling. You need to calculate your total vertical depth. So it is done using these four methods called as minimum curvature method, radius of curvature method, average angle method, and constant build and turn method. So these are the methods that are commonly used to calculate your coordinates and to do all the calculations for your well trajectory. This is just an example of formulas that are used for calculating your coordinates by average angle method. Again, each method has its own formulas, and they give comparable results. So here is an example, and we will calculate this during our main course because of the limited time. But what I also have is an Excel sheet that I will show you towards the end of this course, where I have ways to calculate this. And in real world, you actually use a software to do all the calculations. You have a software that does all the trajectory calculations. But to give you an idea about what goes behind doing all the calculations and using all these equations, which are not really very big, but at the same time, they do have some, multiple calculations and equations. So you have a data like this, basically where a survey was taken after drilling 150 meters. Following is the data from the survey. So you have your coordinates here, initial coordinates, then you have inclination and your azimuth from the first point. You have inclination and azimuth from the second point, and then you have your measured depth. Delta measured depth is like 150 feet that you have drilled. And then you use these equations here to calculate your north, east, and TBD. And then when you add to these values here, you will get your new values, your coordinates, north and east, and your total vertical depth. So this is how it is done, essentially. Now, what else? What do these tools measure? The tools basically measure inclination, azimuth, temperature. You have your gamma ray, you have your vibrations, your bottom wall assembly, and your tool face. So then this is how a typical schematic configuration is for a directional tool, where you have your, now in this case you have your mud pulse telemetry, and you pump your fluid through your drill string, and the returns go from annulus, and that that one is the one that is carrying your MWD signal, and the signal is received here at the pressure transducer at the standpipe manifold, and that pressure is then decoded into a meaningful signal. So this is what you have as a measurement while drilling. But we also have logging while drilling. Now, what is the difference between measurement while drilling and logging while drilling? These terms are loosely and interchangeably used. So to be very clear, what measurement while drilling measures are these parameters, okay? They measure inclination, they measure azimuth, they measure temperature, gamma ray, vibrations, bottom hole pressure, and tool face. So these are some of the things that MWD measures. But you also have logging while drilling, and logging while drilling is, basically a system to acquire logging data. That is, in addition to what you just saw, you actually can get information about lithology, porosity and permeability, formation dip angle, presence of fractures, and hydrocarbon saturation. So you get a comprehensive set of data using LWD, and LWD gives you an opportunity to measure all this while you're drilling and before you reach your section TD. The advantage that you have here is that now these are the measurements that were traditionally done using wireline logging. So with the advent of LWD, you can now measure all this information. You can get all this information, and more than this, while you're drilling, without having to, spend time for electric logging, which is a time-consuming process. So when you reach the section TD, you kill the well or you displace the well with a heavier mud, and then you go with a few logging runs. So that's a time-consuming affair. So to avoid, if you can avoid that by just incorporating logging while drilling in your BHA, then you can cover those logging objectives while you are drilling. So typically, this is how a logging tool schematic would look like. It has, gamma ray, resistivity, and you have a drilling mechanics sub where you measure your vibrations, your pressures, temperatures. On the top here, you have your density and neutron tool, which gives you an opportunity to calculate porosity. Gamma ray will give you differentiation between your shale and sands. Essentially, you can get some idea about the lithology. Resistivity also has the same potential, but also you can measure hydrocarbon, water saturation in a particular formation. So these are the array of tools, is what they call, are used within your BHA to give you meaningful information about your lithology. And common other measurements are annular pressure, vibrations and shock, equivalent circulating density, equivalent static density. So these are some of the measurements that are done with LWD. Very useful data, very meaningful information that otherwise is difficult to is only available when you calculate using some equations. But now with this development and progress in LWD, you can actually measure them physically with the tool that is part of your drill string and is there right in the around the zone of interest. And drill string, which is one of the most important components in our directional drilling objectives. In that, the most important way, we spoke about drill string and BA, we spoke about BHA components, but drill pipe is the most important thing. So it is the largest part of your drill string. And the objective of drill pipe is to support your bit and BHA. Its purpose is to transmit rotational motion to the bit. So when the drill pipe rotates, it is typically connected to the top drive. From there, it transmits motion and rotates the bit. If you're using a motor, then it acts as a support because then it doesn't rotate, but the motor will rotate and drill pipe will typically just transmit your motion, and that motor will take care of the rotational part using drain fluid hydraulics. And most importantly, acts as a conduit for drilling fluids to be circulated from surface to downhole. So there are 3 grades, in any drill pipe configuration. There are about 4 grades, not 3, but 4 grades. And they are basically depending on the strength of the drill pipe. They're classified, as you can see, a minimum yield strength, maximum yield strength, tensile strength, and elongation. So if you want to use higher grade drill pipe, then it is going to be expensive and the need has to be justified. That application engineering is something that we're going to discuss But to give you a general idea, typically when you are having a large, deeper well with more weight on the drill pipe, as you go deeper, the drill pipe needs to suspend, a bigger pipe underneath it. So the grade has to be higher in order to prevent any yield stress and failure. So in other words, as you go deeper and you have longer pipe sections, the drill pipe is also to be for higher grade. It needs to be of higher grade. And in directional wells, as we will talk, drill pipes are subjected to a variety of loads other than just vertical loads, axial loads. They also have torsional loads, they have torque and drag. There are so many different loads that need to be accounted for, and thus the pipe has to be stronger. So now we spoke about hard banding a little bit. Now this is done in order to basically inhibit or prevent friction and wear between the tool joint. This part of the string is the tool joint and the casing. Now why tool joint is because if you see there's got an external offset. This is the drill pipe and this is the tool joint. So tool joint has got, you can see that it is extending out. So that's the first one that will come in contact with the casing when you are rotating, and therefore, or when you are static as well, but mostly when you're rotating, and therefore that can cause wear. So to prevent that, basically hard banding is used, So evaluation of torque and drag with the planned or show trajectory is quite important as a part of guidelines of drill string design. What you need to do is you have to evaluate torque and drag. You need to calculate buckling severity, side load force, slip crush of a segment or a pipe string, and then of course hydraulics, where you should be able to clean the hole properly. You should be able to move all the cuttings out when you're circulating, and also make sure that the friction pressure loss is being calculated and it's neither too hot nor too low in order to cause an issue. So that is an important thing. These are some other guidelines that are there for drill string. Basically, that it should meet the mechanical load to prevent any failure. All the critical parameters have to be optimized when you're drilling. And then you have your torque and drag based model. So you need to make sure that your model is calibrated and up to date with the drilling parameters. And pressure drops and pressure drop and ECDs, bottom hole ECDs are important calculations, to need to be done ahead of time before you select your drill string, so that you get the right drill string. If you have a very small drill string, the pressure drops are high. If you have a big drill string, a wider drill string with big tool joints, then pressure drop in annulus is high. So considering all this, you need to balance your design very well to make sure that it satisfies all the requirements and you are not taking unnecessary risk. So these are parameters associated with drill string design. Now vibrations. So vibrations are a very critical, what I should say, critical issue related to any drill pipe. Vibrations have caused failures of drill string, failures of BHA, damage to the bed, and so on. When the drill string encounters vibration, you don't make any progress in drilling. You'll be just rotating in one place, causing a severe loss to the oil company. Why? Because of not being able to achieve the desired ROP or desired drilling depth. So these are the points that are important to analyze as we go. And as I said, they are one of the major causes of failures of drill pipe. Drill pipe is receives a lot of cyclical load, makeup, braking, and so on. So drilling vibrations are the component that needs to be studied, before you proceed further. Now, the types of vibrations that we typically encounter are like lateral vibrations, and axial vibrations, and torsional vibrations. So these are the three vibrations. And again, we will discuss this all in details as we go along in this course. The three vibrations are highly critical, and to analyze and make sure they are detected, there are tools, but also there are some surface indications that you need to keep in mind before arriving at a conclusion that your drill string is experiencing vibrations. And if they are indeed experiencing vibrations, then it is important to immediately stop and do a course correction. There are other type of loads that a drill pipe carries, and that is called a sinusoidal buckling. So when a drill string is subjected to increased or compressive loads, then it undergoes several changes. Now, the drill string is the first stage of buckling. In this case, is sinusoidal buckling. Then you have helical buckling, and then the third part is lockup. So when you go from sinusoidal buckling, or when you go from sinusoidal buckling to helical buckling, it's like a second phase. You move from one to another, and it should be avoided all means. When the compressive loads increase further, this can lead to lockup, meaning the string gets jammed in the open hole in a helical manner. That should be taken into account when we do our design. And that's pretty much it. I just wanted to discuss these methods. I will share the Excel sheet with you that we are planning to use. So what we have is some exercises that we will do, not today, but during our course, because we'll have more time. And that will be calculations of different parameters when you do the directional planning. So for example, here is the same example that I had in the book. What we have is formulas and a schematic that shows you how. This is your service station 1. This is your service station 2, and you drilled from 1 to 2. How much you have drilled? 150 feet. Then now you have your at service station 1 you took an angle. Service station 2 you took an angle. That's reflected here. See, it's 5 degrees, 15 degrees. The diagram is not exactly representative, but at service station 1 you took 5 degrees. Service station 2 you took 15 degrees, and you also took the azimuth. What was azimuth? Here you see in the yellow, that's azimuth, yellow angle. The red one is the inclination, and the second one is azimuth. You'll always have these two for calculations. So what we have here is your azimuth is 10 degrees at service station 1, and your inclination is 5 degrees at service station 1. And then as you go along, you drill 150 meters, and then you stop, and then you take another survey. And at that time, you get these readings. This is how you typically progress in directional drilling. That time you get your inclination as 15 degrees, azimuth as 20 degrees. Now we need to calculate the new coordinates and your TVD. So these are the mathematical equations for north, east, and south. You have your average inclination, average azimuth that we have calculated here from these simple mathematical equations. And then you substitute them in this equation, multiply them with delta measured depth, which is 150. That is the difference between measured depth at first station and measured depth at second station. So you deploy all these values here, and you would get your north, east, and new TVD at your second service station. So this is how you typically proceed, and then you have the other methods as well, which we will discuss, in our course one by one. So there are some other calculations that I would share with you for directional planning, and they will also be discussed during the course. For example, there are calculations of dogleg severity. There are calculations of horizontal displacement. So a number of calculations will be used, to get a practical idea about how it is done, and what we do as directional drillers, as engineers. Now, I think we are almost approaching the end of today's session. It's